Hello my dear students. Last class in part 1 we discussed about the difference of interference and diffraction and definition of diffraction. Today class we are going to discuss about the Fraunhofer diffraction at a single slit. We already discussed there are two types of diffractions, that is one is Fraunhofer diffraction and second one is Fresnel diffraction. In Fresnel diffraction we don't use the lens. In Fraunhofer diffraction we will use the lens. So before going to the class we can see a small video of diffraction. See, here it is the light source and here it is the aperture or obstacles or slit, whatever it is, and here it is will be the screen. See how the diffraction phenomena will happen.
Wave-like characteristics.
See,
and the two
the
main
wave
types
nature.
of diffraction.
The wave nature.
When light waves encounter an obstacle or pass through a narrow opening, the light waves bend around the edges of the obstacle or opening and spread out. This phenomenon is called diffraction. Diffraction can be observed with all types of waves, including sound waves, water waves, and electromagnetic waves such as light. Diffraction of light demonstrates the wave-like properties of light. When light waves encounter an obstacle or slit which is comparable in size to the wavelength of the light waves bend around the edges of the obstacle, creating a pattern of alternating dark and bright regions known as diffraction patterns. According to the Huygens-Fresnel principle, every point on a wave front acts as a...
See, according to Huygens principle, every point on a wavefront acts as a secondary source of waves. What is that? Every point on a wavefront acts as secondary source of waves, which is acts as a secondary source. So, the wavefronts acts as a secondary source.
Secondary source of waves. These waves from different parts of the opening interfere and produce the diffraction pattern on the screen. This pattern indicates that light is behaving as a wave, interfering constructively at some points and destructively at others. The bright bands are regions of constructive interference, where the crests of the waves meet the crests of the other waves, which means that the waves are in phase and add together to create a larger wave. For destructive interference to occur, the waves must be out of phase by 180 degrees. This means that the crests of the waves must meet the troughs of the other waves. The amount of diffraction depends on the relative size of the wavelength of light to the size of the opening.
So, the diffraction pattern will depends on the slit of the size, that is the slit, the barriers or the obstacle of the size will depend on the wavefronts. So, the size of the slit depends the size of the wavefronts.
If the size of the opening is much larger than the wavelength of light, the diffraction will be almost unnoticeable. However, if the opening is comparable in size to the wavelength of light, diffraction will be significant. The smaller the size of aperture or obstacle and the longer the wavelength, greater will be the diffraction. The greater the size of aperture and the shorter the wavelength, lesser will be the diffraction. There are two types of diffraction, Fresnel and Fraunhofer. In Fresnel diffraction, the light source and the screen are relatively close to the obstacle.
So, in Fresnel diffraction, the distance between source and the screen, that is finite distance. But in Fraunhofer diffraction, the source and the screen, that is distance, is infinite distance. And in Fresnel diffraction, the shape of a wavefronts or are cylindrical in shape or spherical in shape. But in Fraunhofer diffraction, the wavefronts will be plane.
This proximity results in complex diffraction patterns. On the contrary, Fraunhofer diffraction occurs when the source and the screen are at larger distances from the obstacle. Fraunhofer diffraction patterns are simpler and easier to calculate.
Stock market trading apps are currently.
After the small video, then we are coming to Fraunhofer diffraction at a single slit. And one more slit is there in Fraunhofer diffraction, that is double slit, and N slit also is there. In Fraunhofer diffraction, there are two types of diffraction, single slit and double slit. First, coming to Fraunhofer diffraction at a single slit, see here we can observe the diagram. The edges A and capital B are the edges of the slit, and between the edges there is a slit, that is width of the slit. And the diffraction, see the diffraction phenomena will happen through the lens, that is which is passed on the and appears on the screen, that is P and O. Here it is, we are using lens. Okay, here it is the screen. Then coming to here from it is the source of the light, and in down there is another diagram from source to slit. It will be infinite distance, and these geometrical shadow region will happen by the diffraction pattern. The intensity of waves will appears according to the wavefronts. Okay. Then coming to the description of Fraunhofer diffraction, let us consider the rectangular aperture. Aperture is nothing but a slit here. Okay. Aperture whose length is large as compared to its breadth. Let a parallel beam of wavelength be incident normally upon a normal slit of AB, and each point of AB sent out secondary wavelet in all directions. We already discussed about how the secondary wavelets will happen in the short video. These rays proceedings in the same direction as the incident rays and focus the point at O, and which is diffracted at angle theta. Here it is the theta's angles from diffracted light to wavefronts. Here it is theta, and here also it is theta. And another angle we can observe here, that is a right angle triangle, that is delta is here, and the width of the slit is small a. We are considering width is the small a. Then the path difference between AP and BP. The path difference, what is AP? That is from the edges of the slit to first wavefronts, that is AP, and the second edge of the slit, that it will be BP, is calculated by it is perpendicular to the B and K, that is BK. Then according to the figure, the path difference will be sin theta A. Sin theta, that is sin theta, we have here rectangular angle, right angle triangle, that is sin theta equal to BK by AB, that is BK. What is the AB? AB is the width of the slit. The distance of AB, that is we are considering, that is width of the slit, that is we are considering here AB is small a. Then we can take the BK, the delta will be, the angle will be A sin theta. What is that? A sin theta, because of right angle triangle. Then coming to phase difference. Coming to phase difference, that is delta equal to 2 pi by lambda into triangle. Triangle means we are considering the angle here, that will be 2 pi by lambda e sin theta with combination of width. And next one, by assuming we have a polygon arc. A polygon arc, it's a simple concept, that is polygon arc. That is, we have like triangle with rectangular, the wave function will forms. That is delta equal to arc by radius, NA naught by r, and r equal to NA naught by delta. So this is the formula for from the polygon arc. Then from the polygon arc we are going to applicable here, that is perpendicular, that is CN is drawn from the center of C, an arc of the line which will divide the amplitude R in two parts, that is triangle ACN and triangle BCN. Then we can do the equation part, that is sin delta by 2 equal to, that is R by 2, that is AC. Then it is converted into the AC equal to BC, that is small r, because of we are representing R will be the resultant wavefronts. The R equal to 2R sin delta by 2, and putting the values in small r, then we finally got the equation R equal to NA naught, that is NA naught sin alpha by alpha. What is sin alpha by alpha? If we are assuming means, that is delta by 2, we can take the alpha, again the lambda by pi by lambda a sin theta, and the intensity is directly proportional to the amplitude square. Amplitude, that is resultant amplitude. I is directly proportional to r square. Then we can write the r square into the value I equal to I naught sin square alpha by alpha square, where it is I will be I naught n square a naught square. Then the intensity distribution by single slit diffraction. We have two concepts, that is minima and maxima. Minimum is nothing but a minimum and maximum is nothing but a maximum. But in scientific manner we are call it as maxima or minima. Okay, coming to the intensity distribution by single slit diffraction, first one will be central maxima. The central maxima, we are going to take the central point P on the screen, theta equal to 0. If theta equal to 0, almost alpha equal to 0. Here we are neglecting the alpha, but not it is completely 0. By we are explaining central maxima. Maxima is nothing but 1 and minima will be nothing but 0. Maxima will be 1 and minima will be 0. But in degrees we are taking theta equal to 0 and alpha equal to 0. But alpha is not and completely 0. And I equal to I naught sin square alpha by alpha square equal to I naught. So that is the limitations between from alpha to 0. That's why we are saying here alpha is not completely 0 and is not negligible. That is sin alpha by alpha, then it is 1. That is P will be maximum, that is central maximum. Then coming to principal minima. For the principal minima, intensity should be 0. What is that? Intensity should be 0. Then we can take the sin alpha is 0 and A will be plus or minus alpha equal to plus or minus n pi. So here what is the n? N will be from 1 to up to n number of intensities. Then coming to secondary maxima. Secondary maxima, we can see the diagram here. See, this one will be the center and here it will be the minus plus values in x and here it is will be the minus. That's why we are representing plus or minus pi values. Plus or minus pi values. The directions, these are the intersection points. Intersection points, the cross cutting of intersection points, it will be y equal to alpha we are considering, and the intersecting points, here it is cut the line that we are representing y equal to tan alpha. Then coming to the differentiate of the secondary maxima, we are differentiating intensity equation with respect to alpha and equivalent to 0. It is not completely 0, but it is equivalently 0. That is why we are differentiating the intensity. That is according to derivative parts, that is di by d alpha. So we can take it is equivalent to 0, that is equal to 0. Then d by d alpha, you can substitute the I values here in previous slide, that is I naught sine square alpha by alpha square equal to 0. Then we can simplify the equation. I naught equal to 2 sin alpha cos alpha into 1 by alpha square in minus sin alpha by alpha cube equal to 0. This is the derivative formula from the differential equations. Then coming to take the common here, that is I naught 2 sin alpha by alpha cube alpha cos alpha minus sin alpha equal to 0. Here take the common values. A cos alpha minus sin alpha equal to 0. Then cos by sin, that will be tan. We can take the alpha value, that is tan alpha. Okay, this is the condition. For the secondary maxima. Then it is plotting to the graph between y equal to tan alpha and y equal to alpha. Here y equal to alpha, then y equal to tan alpha. The point of intersection of two curves, that will be position of secondary maxima. These positions will take alpha 1 like 0, alpha 2 will be 1.43 pi, alpha 3 will be 2.4 pi. At the same time, another formation, that is alpha equal to plus or minus pi by 2, then alpha equal to plus or minus 2 pi and alpha equal to plus or minus 3 pi up to alpha equal to plus or minus n pi values will come according to the. Then take the alpha values. Here take the alpha values, that is pi by lambda a sin theta, then plus or minus 2n plus 1 into pi by 2. Here we can substitute the values, that is I value I naught sin square 2n plus 1 pi by 2 by 2n plus 1 whole square pi square by 5, because we have a 2 pi's here, that is why pi square, and finally I will get 4 I naught by 2n plus 1 whole square pi square. Then see the I, how to the intensity variations, that is first intensity, second intensity and third intensity, that is I equal to I naught, I1 equal to I naught by 22 and I2 will be I naught by 61. So it will increase on the order of the intersection points. Then coming to intensity distribution by a single slit diffraction. Here we are considering the peak of the line, that is intensity max. The peak of the line, it is intensity max. The first one, it will be the, see, here the biggest curve, here it is shows big curve, that intensity, that is central maxima, and second one will be the secondary maximus, that is I max, I1, I2, and here also same, that is intensity is max, in left side that is minus values I1, I2, and if you observe here the pi value 2 pi, 3 pi, here it is this side minus pi, minus 2 pi, minus 3 pi. So what is the difference here? Here the minus values will consider as the principal minimas, and here it is the values will be secondary maxima. This is the main difference between the intensity maxima, that is in secondary maxima, and principal maxima. See, the intensity distribution curve of the Fraunhofer diffraction in a single slit. I hope you get it. The next one, we are going to find the width of the central maximum. So here the width of the slit is very important, because of it only width depend the wavefronts, how much the width wavefronts will happen based on the width of the slit. The wavefronts will form based on the width of the slit. If the width of the slit will be increased, the wavefronts also increase. The geometrical shadow region will also increase. The width of the slit will decrease, and wavefronts also, through the diffraction, the wavefronts also will form in small. The width of the central maximum can be derived as the separation between the first minima in other side of the central maxima. If first maximum, that is distance x, that is, we can observe the diagram in first diagram. Here it will be the P0 and here it will be the P1. That will be the distance between two wavefronts, that will be the x, that is central maxima. We can take the weight, that is 2x. We know that already, that is A delta sin theta equal to n lambda. A sin theta equal to n lambda, and for there is another conditions for m lambda also. So that is a different kind of situation. Here it is different condition of situation. See, here it is the width, that is A, and the distance between slit and the screen, that is we considering the distance D. And here it is one more thing, F will be the focal point from the lens to screen. Sometimes we can say from source to, here it will be the source, from source to, here is one more lens, that will be a focal point, we consider as a focal point. Then coming to equation part, if you take the n equal to 0 and theta equal to theta 1, so if sin theta 1, and that means we are representing angle 1, that is theta 1, plus or minus lambda by A, that is wavelength by width. So from the diagram, the tan theta 1, that is x by d, is equivalent to x by focal point. Then that is lambda by A equal to x by f. If theta is very small, that is sin theta equal to tan theta equal to theta. Okay, sin theta, tan theta equal to theta, that is the small. That is why we are writing the equation W equal to 2 lambda f by A. A will be width. Next one. Coming to Fraunhofer diffraction at double slit. Fraunhofer diffraction at double slit. The difference between Fraunhofer diffraction single slit and double slit. In Fraunhofer diffraction, we are using only one slit. In double slit, we are using two slits of the lens, two slits, that is two barriers, two obstacles of the diffraction pattern. Now, considering the diffraction pattern, we are arranging two slits which having the width that is D and separated by the distance A. Sometimes some diagrams we are differentiating the width of the slits AB, Sometimes some diagrams, some textbooks it explains the two slits, the widths will be AB and here it is DA we are taking. The resultant fringe pattern will then consist of the interference pattern due to the two slits. In diffraction single slit, we don't have interference happen in third phase, but in diffraction double slit, the two slits happen to the interference pattern due to the two slits. Each individual slit will also produce a diffraction pattern. So there is a two slits and these two slits will produce as a each single slit will produce diffraction pattern. Clear? Then the diffraction pattern between the two interfering waves will be PD equal to A sin theta. What is PD here? The distance from the source 1, source 2, the distance between PD, that is path difference between interfering waves, path difference, that is A sin theta. The path difference, see, if you observe here it is a right angle triangle and here is the pattern, that is the path difference PD equal to A sin theta. Next, the Fraunhofer diffraction, we can total the total intensity fringes pattern. That is, if you observe the diagram here, here it is the first curve or first wave will be diffraction envelope and the second waves are interference pattern. So according to this we have a formula, that is we can substitute the values in previous equation, that is I naught cos square pi a sin theta by lambda, and we can cancel the pi d sin theta by lambda and we can get the values, that is the equation. The first term of above equation is called the interference factor and second term is called the diffraction factor. So in double slit we are explaining the interference pattern at the same time diffraction pattern too. If 0 of diffraction envelope coincides with the maxima of interference pattern. Okay.